last class when we left off, we started an introduction of these things called binary trees. And we're going to use trees and similar things to it the rest of the class. So this has become kind of important. So if I said to you, from what you learned the other day, if I gave you these random letters, could you build a binary tree out of that? Could you set it up? Could you build it? And some different things that are going on. Well, quick reminder, H was going to actually be my root node. If I remember right, this is a tree. When I flip it upside down, I have the root at the bottom. I have leaves at the end. So we start putting together some terminology. We have the root node, and we had leaves. Okay. When I built my binary tree, I came out one of two directions. So it's I have two choices, which takes me back to binary, a 0 or 1. A is less than H. R is greater than H. The next R, how do we say we're going to handle ones that match? We're going to put it to the left or we're going to put it to the right? Anybody?
To the right.
Doesn't matter to me. Doesn't matter to me. So our rule is to the right. We did have something called binary int tree that I gave you last class. I didn't know if anybody happened to look at it and see what's going on. Okay, where does the I go?
To the right.
To the right of H?
And then to the left of R.
To the left of R. Okay. I always need to remember when I'm building these to go wide. All right, so we just did I. Where does S go?
Right of the bottom R.
There you go, right of the bottom R. Where does B go?
Right of A.
Right.
To the right of A. Okay. U.
Right of S.
Right of S. Another R.
Would that be to the left of the S?
Finally, a G.
Right of B.
Right of B. So I have G in there. Okay. So let's see. I have some things going on here. This is actually pointing to null. This points to null. This points to null, 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 and null. Lots of nulls. Okay, so some terminology. We just mentioned root. We mentioned leaves. How many leaves are there for this? Take a guess.
11.
I hear 11. Do I have another choice? Well, the leaves are going to be down here on the end. Anything that points to two nulls is a leaf. So there's 1, 2, 3, 4 leaves. The root node is H. What else do we have going on? We have terminology. We have a child and a parent. Okay. I take a look at R. R is a parent to I and to R. R is a child of H. We mentioned the other day something about subtrees. Okay. Does H have a left subtree? That's everything over here. Does H have a right subtree? That's everything that's over here. We're going to talk about the height. That's the number of levels. What's the height of this tree?
4.
I'm going to come down 1, 2, 3, 4, 5. Now that's what I'm going to refer to as the height. level 1, level 2, level 3, level 4, and level 5. I have seen people say that the height is only 4 because you don't count the root, but I don't like that, so we're going to go with it. And then finally, we had pre, in, and post. We worked on traversals for this. Okay, pick one. Pre, in, or post?
Post.
Post, right? Because in should be easy, right? In should be Harrisburg. Okay, so post was left, right, and then node. All right, let's see if you can come up with postfix for this.
G.
G. Anybody?
B and then A.
GBA. Okay. So I tried to go left, I couldn't. So I tried to go right, I tried to go left, I couldn't. Try to go right, try to go left, I can't. Go right, I can't. So I go back to node. Then I go back to node, I go back to node. All right. So now I'm back up here. I took care of the left. Now I need to take care of its right. I come to here. What do we got after that?
I.
Yep.
And then R.
This R, yeah.
And then U.
U,
And then go back up the tree
E,
back.
S,
R, R, H.
R, R, H. Okay. Questions? Okay, so these binary trees actually have a lot of uses. And for example, I could do one of these. I could, in here, I don't have to just have a letter. This is some sort of key field in here. It's what we're going to be looking at, and then it's going to determine, do I go left or do I go right? For example, some of you may have seen a decision tree, and a decision tree might be something like asking a question. I'm thinking of an animal. Okay, and the first question I might ask is land or air? So we're eliminating all fish. We're going land or air. So if you said land, I'd come down this way and ask another question. You said air, I'd come down this way. And it's one of those where you can guess how many in, it's one of these things. Did you ever see this? 20 questions? Anybody ever see this game? Anyhow, to ask a question and you pick a yes or a no and it goes down and eventually it'll guess what you were saying. So for example, if it's on the land, what question might come next? 2 feet or 4 feet, and then you pick one and go here to here. And eventually you can keep asking questions until you find out what the actual answer is. So you may see some sort of decision tree going on here. Another thing that you might see binary trees used for is this bad boy. Look kind of familiar?
Is that a game tree?
That is Morse code. Okay. This is in fact Morse code. So the way Morse code was created, and we're going to look at doing some of this stuff. It's actually really cool when we get to it. But what happens here is, what do you think the 2 most frequent letters were way back when they created Morse code? Can everybody see what this one is?
E.
E and T.
I.
That's actually T. So it's E and T. So what's going on here is, for E or for T, since they're used the most, they only have, to represent an E, it's a dot. To represent a T, it's a dash. So something way down here like X, in order to represent X, you'd need dash, dot, dot, dash. Well, X isn't real popular, so it's okay to have a length of 4. Because remember, part of this idea was to send a message as quick as possible. You know, here's E and T. Your next row of letters are I, A, N, and M. So again, we're trying to send a message as quick as possible. We have it coded. We can do dots and dashes, and you see the use of a binary tree. Now, how did they do this? My bet is they went and looked at a whole bunch of documents and counted all these letters. And E came up the most. T came up the second most, and so on across that next line. Now, why down here we have some leaves, you know, and why some come up short and one actually go a little longer, I don't know. That would be the whole study into Morse code. But we're going to take a look at, in a week or two, doing some work with this, creating our own, and how it comes out. And it's actually pretty cool. It's pretty cool. Morse code, you have dot, 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 space, dash, 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 space, dot, dot, dot. Well, the spaces are the key to let you know between each character. But when we take a look at this, we're going to try to eliminate the spaces as well and keep it as short as possible. Keep an average character length as small as possible. So if I put a word out, you know, and it's a dot and a dash and 2 dots, what's the average number of paths to each node? Try to keep that number down. So that's kind of cool in my opinion. So that's another example of a use for a binary tree. Some definitions. See where we're at. Binary tree. Okay, we talked about doing Harrisburg. Terminology: root node, child node, leaf node, parent node, subtree, pre, in, and post, and height. We should be starting to get good with the traversals. Decisions tree, binary tree. Okay, a complete tree. Complete tree is one where each level is filled from left to right, but the bottom doesn't have to be completely filled. So if I threw this guy up in front of you and I said, okay, taking a look at this first binary tree, is that complete? Is it filled top to bottom, left to right, but the last row is not completely full?
Yeah.
Yes. Is this a complete tree? Well, yeah, all 3 of these actually are a complete tree. If I look at this example, you can see where this node is missing. So it's not going to be complete. Up here, this node is missing. So it's not being filled from top to bottom, left to right. And clearly this guy is a giant mess. So again, the definition of a complete tree, it's filled from top to bottom, left to right. And we'll be doing some work dealing with complete trees. Okay. Another definition I have here is a balanced tree. And it's a binary tree where if I start taking a look at the left tree for each node and the right tree for each node, counting their levels, that the levels only differ by at most 1. And I think that's probably easier to look at than to actually say. Where are my examples? I don't really have a good example. I do have an example. Is this a complete tree?
No.
Is it a balanced tree? No. Let's take a look at H. What is the height of H's left subtree?
4.
To the left of H, we're going to go 1, 2, 3.
Oh.
What is the height to the right of H? 1, 2, 3, 4. So 3 minus 4, that's -1. That's a -1. That one's okay. The heights only differ by 1. If I come to A, what's the height of its left subtree? 0. What's the height here? 2. 0 minus 2 is what we're going to call -2. And it's not a balanced tree. Okay. What would the R come out to be? One minus 3, negative 2. This R, 0 minus 2, that's also a negative 2. Eventually, we're going to learn how, when we put these letters into a tree, like Harrisburg, we get this. And if I did the in-order traversal, I would get Harrisburg. We're going to look at a way, as we add them, we may be making changes without messing up the integrity of the tree, without screwing up our prefix, postfix, infix kind of deals. Okay, so this guy definitely is not a balanced tree. Okay, so up to this point, we've been talking about linked lists and arrays. And whenever we get a new concept, we do some comparison between linked list and array. The binary tree just kind of comes true to form for a linked list. But let's talk about if we could represent this as an array and work with it as an array. Okay, so I have the letters M, T, E, C, U, P. And I need to keep this binary tree concept. Can I create a way to use arrays instead of linked lists? Well, I'm going to start out by building the tree. I have an M. I need to remember to go wide. I have a T. I have an E. I have a C. I have a U. I have a P. And I have an O. Did I do that right? Say yes.
Yes.
T is to the right, E is to the left, C is to the left of E, U is to the T, U, V, right? P is to the left of T, and O is to the left of P. I think I have it right. You all agree? Galen said yes. Okay, so here's how we're going to make this guy work with an array. I'm going to call my root 0. I'm going to call the E 1, 2, 3, 4 is null. 5, 6, null is 7, null is 8, null is 9, and 10, and 11 is O. So if I can do this, I can now put it into an array. So I'm going to use my M. In 1 is E, in 2 is T, 3 is in C, P is in 5, U is in 6, and O is in 11, 15, 14, 13, 12. O. Okay, so I'm actually able to store these in an array. Now, what happens? Well, as soon as I start looking at the array, I realize that I may be wasting a lot of memory. What would be good for my memory? If this tree was more B-word.
Balanced.
Yeah, if it was more balanced, and if we build it in a way to make it more balanced, I'd be wasting less space. So, you start to see the levels. This first level is 1. Here I need 2. Here I need 4. So as I'm going down the levels till I get to this third level, if I filled them all up, I would only need 15 array memory locations. So you start to see some kind of pattern going. Okay, so if I'm looking at a tree and I say, hey, E, who's your parent? M, who's your children? C and a null. Okay, that's fine. So we can look, and it makes it really clear. The M's, we got the M's right is T, and so on. It's kind of hard to go backwards. But if I come down here and I'm looking at who is my parent? Where's my parent located? So if I take P, and which is in position 5, where is its parent located? Well, where's T located? So if I'm given 5, where do I find my parent? If I'm given 3, my parent is in location 1. If I'm given the number 1, my parent is in location 0. Well, hopefully I've taught you by now that 5's parent is 2, 6 parent is 2, 3's parent is 1. I'm just some test data kind of idea. 1's parent is 0, 2's parent is 0. So if I give you a memory address, what algebra do I need to find the parent? I'm bursting to tell you because I know the answer. Where are my algebra people? Where would 14's parent be in my array?
Doesn't it have something to do with 2 to the nth power?
No, yeah, but kind of in reverse. So
Yeah.
again, if I give you a parent of 5, if I give you the number 5, how do you get 2? If I give you the number 6, how do you get 2? If I give you 3, how do you get 1? So 3 and 4 both have a parent of 1. 1 and 2 both have a parent of 0. Should I tell you? Should I tell you? Somebody think they can figure it out?
I'm lost.
You're lost? All right. N minus 1, integer division 2. So if I'm at 5, I subtract 1. 4 integer division 2 is 2. 6 minus 1 is 5. 5 integer division 2 is also 2. So in order to find the parent, what did I say, 14? This parent would be 13 divided by 2, or 6. Its parent would be U. So if I kept going, here's 12, here's 13, here's 14. 14's parent would be U. Somebody say, oh.
Oh,
Okay, good. All right. So that's the first part. Now the second part is, if I give you a parent, where is its child located? Well, it's going to have 2 children. So let's see. If I go to 0, its children are 1 and 2. If I go to 1, his children or her children are at 1 and 3, at 1 or 3 or 4. 2's children are at 5 and 6. 3's children are at 7 and 8. Looks like I'm going to need 2 equations here.
Wouldn't it be just 2n and then 2n plus 1?
Really close.
Oh, yeah.
2n plus 1 and 2n plus 2. So if I said, where are P's children? You'd be telling me 11 or 12. If I look up here, it would actually be 11 or 12. So if I was going to work with an array, that's how I would have to find the parent or the child, by using these formulas. But as you can see, it is possible. I could do a binary tree representation using an array. Okay, questions? All right, so last week I did give you int binary tree. And what I want you to do today is I want you to add 3 more functions to it. And I think this is good practice to get you up to speed with that binary tree. And, again, we're using the integer one, it's linked list. I need you to count the number of nodes. Okay, so if I look back to like Harrisburg, it's how many letters there were. If I look up to this tree, 2, 4, 6, 7, I need to count the number of nodes. Okay, that's the first one. Count the number of leaves. What did we say a leaf was? A leaf was something that both, go ahead.
I had 2 nulls on node.
Yeah, it had 2 nulls, right? It had 2 nulls. And finally, can you count the tree height? So if I looked at this guy, 1, 2, 3, 4 would be the tree height. When I first mentioned these, some of them sounded really easy. And now you're going, maybe not, maybe not. While loops are fine. If you think you can pull off a recursion, that's fine as well. But that's what we're going to work on, doing these 3. And then you also will have time, as I said a moment ago, to talk within your group about how you want to meet up. Do you want to do it all by emails? Do you want to do it by a Zoom meeting to work on it? Do you want to go to Starbucks and get started because you all live close to each other? Do you want to go to Buffalo Wild Wings so you can get wings or something? So you're going to decide how you want to do this kind of thing.